started. Before we get into, so this is going to start off with like a 10 to 15 minute PowerPoint where I kind of just, lay the groundwork so everyone understands what we're going to go over. Then we're going to go into an interactive, Jupyter shell where we will be coding together. I just want to preface, this is the first time running it live, so bear with me. And then after that, we'll go into a little bit more detailed notebook. This is all on GitHub that I'll link to at the end. But before we get into the actual content, let me share my screen. And if everyone has, like you said, a Jupyter notebook, Colab, any kind of notebook environment, and make sure that you guys have the dependencies. So pip install, you're going to want Lale, AIX 360, pandas, and matplotlib.pyplot. And if you put the bang before it, it will run it in the cell. You can also do this in terminal, but you want to make sure you have these 4 libraries. And then the last thing you're going to want is, oh my goodness, sorry, the UCI. You want this data set, and you can just download it from the data folder. It is called the bank marketing data set, and you put UCI, and it will just show up, and you're going to want the data folder. And within that, you're going to use bank additional full. With that being said, I'll repeat it again before we actually start coding. I just wanted to give everyone a little bit of a blanket statement so we can get going, and hopefully everyone can get these 2 steps done before we actually start coding. My apologies for not having this sent out beforehand. But we decided we'll do it live. So with that being said, I'm going to go into PowerPoint. So. All right, cool. So here, let me get this out of the way. Awesome. So yes, everyone is here to discuss explainability, data science, and explainable workflows, and what this actually means and how it's going to impact you as a data scientist, an IT professional, data analyst, to help make your explanations more suitable for your stakeholder, manager, end user, and fellow IT professionals. And the way we're going to be doing this is through open source software and a little bit of theory behind why we're actually utilizing these softwares and work patterns. So feel free to drop questions. I don't have a second monitor to look at, so I'll do my best to get to them as quickly as possible. If it's something urgent, maybe Tim can flag me and let me know that something's up. But let's get into it. So yeah, like Tim said, community.ibm.com, there's a global data science community there. I recommend you join there. You join that community. It's going to let you know, what we're up to, if, where talks are going on. We do giveaways and things of that nature. And it's also a place for you to come and interact with, like-minded folks, people who are interested in, similar topics to you or maybe different topics. And you can post, you'll see what IBMers post, everything in between. It's just a good spot to go and do a daily check-in to see if what's the latest and greatest in data science. I always start with these 3 quotes. So if anyone's seen any of my talks before, this is nothing new. So there's popularized Mark Twain quote, which there's 3 kinds of lies. There's damn lies, and then there's statistics. That one's pretty self-explanatory of what that actually means. Then we have the all models are wrong, but some are useful from George Box. And then the one we're kind of focusing on is why you do that. And hopefully, by implementing these explainable workflows, we will be able to mitigate that question even being asked, because what we are doing will be naturally, it will resonate, using this tooling and this workflows with people before, they feel the need to ask that question. So why are you here? This is one of the graphics that you will be capable of producing after this this tutorial. I'm not going to necessarily explain what this is right now. The idea being, stay here and you'll see it. Probably 10 minutes we'll get to actually coding this. But this is one of the augmented tools you can use in the explainable workflow that's going to allow you to have a better understanding of what you're doing and relay it, in a more timely and transparent fashion to, once again, stakeholders, managers, and users. So what do I mean by augment your work? This is the most text you're going to see on any of the slides, but I'll let you guys read through them. But the ones I like to, really make sure that I'm getting through to everyone is this is going to give you more time to develop an understanding of why you're doing the work that you're doing and why things are occurring the way they are, not just how you do it. So the idea being, why did you use the principal component analysis rather than how you implemented it? They're both important, but the why is kind of the focal point of where things can, become a little bit blurry. And then augment your ability to deduce where things go awry, debug why, and resolve with other data scientists, and then reduce the overall time to reach a solution while increasing and retaining your ability to do trustworthy and transparent work to the extent that you can. I like, so this is kind of just terminology, but these are things I like to delineate because I think it's important. So this is the Merriam-Webster's dictionary definition of what the word interpret means. The way we're going to use it is interpret is it's a static diagnostic. So interpret, you can think of it as diagnosing something. So we're going to, look at it once and diagnose what is occurring, not necessarily why it's occurring. So the idea behind this would be, we are doing an MNIST data set. This is just an arbitrary example, but we're doing MNIST. We understand, these are the criteria we're looking for. These are our features. It's an image data set, and we're going to use some kind of convolutional neural net. We get some kind of output. So we get a negative probability of an image being the number 8. We understand that, probabilities should sum to 1 because of softmax. They shouldn't be negative. That would be the interpretation. We immediately see that and we diagnose, hey, there's a problem occurring somewhere in our script, maybe on the data ingestion, somewhere something's going wrong, and we interpret that and, quote unquote, diagnose it. Explaining, the way we use it, once again, Merriam-Webster dictionary definition, the way we're going to use the verb to explain is a dynamic. So like an iterative, or you could think of recursive process of, we got a negative probability, but now knowing that that's occurring isn't enough. Let's try and figure out why it's occurring and mitigate against it, or not mitigate, remove that from our workflow, and then, capture it through comments, or, a code write-up, or what you may do for your work. So that way we don't repeat that misstep, and also doesn't affect our team or our business initiatives at large. And we also keep that, handy, so that way, if a manager, stakeholder, end user wants to know why, to the extent we can, we will explain it to them. So what does this really mean? This is from Dennis Hinton's paper from like 1990s about causal explanations, but really, to sum it all up, the verb to explain is a 3-place predicate. Someone explains something to someone, versus, in its wider sense, causal attribution describes a process whereby one ascribes some phenomenon to its origin. So the first definition is the definition of explain, and then the second one, this idea of causal attribution, that's what we mean when we use the word interpret. So to sum it all up, we define explainability as the ability for data scientists or another IT professional results to be understood and interpreted by other data scientists and stakeholders. This graphic is just something that I like to discuss. This is something you should be doing in like your quote unquote pre-work before you, make requests for data, or, use SQL to pull data, things of that nature, or, scripting. You can kind of think of the different personas you're going to have to explain to, or be explained to by, depending on where you sit on this graph. And, so we have a 3-dimensional graph where the x-axis denotes experience. I just used arbitrary numbers. I don't know what negative experience would look like, but it was just the easiest way to make the point. The y-axis is your technical skill, and then the z-axis is your need. So your need for an explanation. As you can see, a data scientist, which is, hopefully all of you, relatively experienced, pretty darn technical. The need for an explanation may not be of the utmost importance to you because your work is to do data science, not necessarily, report out to the extent that it's beyond your code. versus a data science manager, someone who's well experienced, has high technical skill, and has a high need for these things because they are the one who's ultimately going to, maintain and manage the project and make sure all the pieces fit together come time to, deploy, test, etc. Two other ones that we have here is end user. So an end user may be someone who without any experience in this field. They may not be extremely technical, but they would have high need. And you can think of this in places of like, healthcare, insurance, banking industries. These are the people who are ultimately going to be affected by this kind of algorithmic decision making. And so for them to reconcile, grievances or, confirm even positive outcomes, we need to, put the onus of that burden of proof on ourselves and, be able to build out systems that are conducive to providing an explanation to someone like that. In the same breath, within those fields as well, there's regulators. Someone who may not necessarily be experienced is relatively technical as well and probably has the highest need other than direct feedback from managers and things of that nature. To the extent, if you're in banking, insurance, healthcare, if you can't meet regulatory standards, then you kind of need to scrap your work, and that is just about as bad as it can get. Other than adversely affecting someone with the algorithm you deploy because you think it's working and you weren't able to explain why it's not or capture why it wasn't working. So beyond adversely affecting someone with the work that you do, not being able to meet regulatory criteria is about one of the other, really bad things that can occur. So, if you utilize these workflows, use some of this theory and expand upon it in your own time, you should be able to prevent these things. If not prevent them outright, understand where they are most likely to occur and, put procedures in place to mitigate against it. This is just a research overview. I'll go over this again at the end, but these are just some papers I think it's helpful if you read them. They do provide quite a good insight into, the growth in this area of research, as well as, come up with some of the best standard operating procedures. There's different takes on, what explanations mean within this field from these different papers, but overall, you should come out of it with quite a well-rounded and professional understanding of what this stuff is if you read these 6 papers. I'll link them at the end once again. The last thing I want to let everyone know is where the demos live for this content. So the AI X360 GitHub is listed right here. The Lale GitHub, which is the semi-automated data science routines that we'll be using. And then the IBM Masterclass, which is about 80 minutes of content that I put together with the help of, some other data scientists at IBM that kind of takes you through a full stack example of what this looks like from, data ingestion, feature engineering, model selection and validation, all the way to the explanation. In 80 minutes, it's like 10 3 to 8 minute videos. So yeah, those are 3 places you can go and visit if you feel like you have a craving for explanations. So with that being said, once again, the data set we're going to be using for the example is this Portuguese banking data set. And what we're going to try and do is classify users if their bank term was opened, yes, or not opened, no, and then identify the principal factors contributing to that classification. So with that being said, let me go back to the chat and see if there was any, I don't know where it went. Well, apparently it doesn't want to let me go back into Zoom, so I'm just going to.
Oh, no questions at the moment.
No questions at the moment? All right, awesome. In that case, we will move forward. So, sorry, when I have this stuff up, it makes it difficult to move. All right, so I'm going to assume that everyone was able to run this. I'll leave it.
Actually, if you could repeat that one. Hey, Austin, could you repeat that one more time, maybe a little bit more slowly, just so everybody gets it? And if anyone missed it or hasn't done it yet, if you could just let us know in the chat, that'd be great. Thank you.
With this? Okay, cool. I'm trying to get back into Zoom and it won't let me. drop it in the chat. So Q&A, no. So that's the command you'd want to run. And cool.
Thank you. And then maybe the link to the data set.
All right, cool. So yeah, you're gonna want the data set. I am going to make the assumption that there is some familiarity with Python amongst everyone. So I'm not gonna necessarily explain like the Python code per se. I'm going to explain what we're doing and what we're trying to accomplish, you know, what parameters we're placing where to the extent it's important. But the idea is for you to, you know, kind of see the workflow in real time, understand, because I saw it as an idea, is that this is not going to greatly add, you know, more labor to your work. It's actually just going to serve as an augment. There's a few minor ways of how you would do things differently, but if you're familiar with sklearn, I would argue that this is going to be pretty darn similar, just with a little, you know, some more nuanced steps with algorithm selection and things of that nature. So with that being said, let's import those libraries that we downloaded. And if I'm going too fast, or if anyone needs to ask questions, just throw them in the chat and I will get to those either at the end or as they come up, as long as I'm able to. And then before I pause, I'm just going to read in my data set, as long as it is where I remember that it is. That's not where it is. All right, cool. So I read in my data set, and then just to make sure everyone's on the same page, you should run this and see what I'm seeing. And then, you know, we can treat this like, let's look at our numeric variables. So this is just, you know, the head command. We're going to look at, you know, the top 10. If that's too much, we could look at the top, you know, 3. So here's 3. This is the description. It's kind of difficult to see anything, so I'm not going to do that. That's overkill. But the idea behind this is, you know, just getting familiar with our data so we can do that. So, okay, yeah. So this makes it look a little bit prettier. So our count, you know, how many, make sure they're non-null. Well, if we want to make sure that it's non-null, well, I'll show that in a second. You know, we're looking at our quartiles, the max, you know, value we have for each one, as well as the mean and standard deviation. So this is just, you know, descriptive statistics. This allows you to get a little bit of familiarity, not too fine grained where we're spending a ton of time, but you know, it just allows you to say, oh, I looked at this, and if you see, oh, one of the counts is different, or, you know, I don't know why the mean for age is negative, things of that nature, that would let you to know, hey, I need to pause, maybe go do some data cleaning, talk to my data engineering team, see what's going on, why does the data look this way? That's always important. The last thing I like to run, this is nothing new for you guys, I'm sure, but it just allows you to have some, you know, a little bit, this is just the pre-work, you know, before we actually start, you know, splitting data, treating it or anything, this is kind of what I would do. So now that we've done this, let's set our X and Y variables. So we have X, we have Y, and then, you know, we can just do this. So all I'm doing there is saying, my X is all of my data where my columns are not equal to Y, which is what we're predicting for. And then our Y value is the Y column. And then we're going to use the map function in the dictionary to map it to numbers. So our X and Y, and we can check that we did that correctly by just hitting X. Y is no longer there, and then we can hit Y, and we have all of our values. So we passed that little litmus test. The next step, I'm going to encode the data just so that way I know it's treated and is in a state where we can move forward and do some other things. I mean, we can plot our data, we can do visualization right here, but for the benefit of time, I'm not going to go into that. That's what I'll show you in like the beefier notebook. So instead of graphing or anything, we're just going to go into encoding. So we can sklearn preprocessing, import our ordinal encoder. We do that. We set our encoder. Yeah, get rid of that. Okay, cool. Encoder equals ordinal encoder. This is just, getting the values for it. So it's treated as like an np.array. It just prevents a few issues that can arise. They won't always come up, but I just like to treat it like that. And then we do our transform. Now that we fit on the data, that allows us to call transform. We transform. This is just a placeholder value. You can name it anything. You just name it placeholder if you wanted. And then what we're going to do, this is for a quick visualization we're going to do in a bit, but we do pd.concat. Basically what this is going to do is it's just going to concatenate our data back into its native form, except this time it will be encoded, which allows us to do the next step. Because since we have some string values, if we want to do like a correlation matrix, it's not going to work with those strings because the strings aren't numeric, so you can't do the math behind the scenes, and it will lead to the correlation. So we do that, and then we just cast this as a data frame. The reason we do that is because Lale, the tool we're using for this data set, since we didn't import it from Lale, it doesn't have a native schema to it, but we could build one. So if you pull this from SQL, MySQL, some kind of RDBMS, you're basically going to be able to, embed your schema to your data, and Lale will make use of that, the underpinning schema, to understand these are the different types. So it basically alleviates some of the headaches that can occur when you're using Python because it's a dynamically typed language. And then our columns are X columns. What did I do wrong? Oh, whoops. What's going on? Encoded. So we encoded our values. We can't encode. I did something wrong. This is what happens for me doing it in purpose or in person. But here, maybe we can figure this out together. So we treated this. So let's explain, let's figure out what's wrong. It's an ND array. So if we want to concatenate it, then we need to, let's do pd dot data frame. Right, cool. Sorry about that. That's you guys are the first ones I'm doing this slide with, so just trying to make sure it works well. All right, cool. So we have all of our data. We have 21 columns. If someone wants to make the decision, and Tim can, so for this to be similar to what's going to happen in real life, there is a part of our data set that is basically going to carry almost all of the information. And if you looked at if you have time, I mean, I give you too much time, but if you look at where we download this data from, it tells you this because duration is the duration of a call. And this is directly correlated to a high degree of whether or not someone is going to get approved for a loan. The problem with this is you do not have the duration of a call before the call occurs. So if we're trying to, do predictive, if we're trying to do classification where we not only predict something, but then we take action of, categorizing it, if there's unknown information that we use to train our model, when it comes to runtime, we won't have that information. It's going to fail. So, that's not necessarily explainability. That's just, understanding your data sets and understanding, downstream effects. But it is explainability because, if we just ran our models blindly, we'd get great results. But the idea is, we wouldn't understand why without doing a little bit of this groundwork, or if we just didn't read the instructions from the baking data set. So we can drop it. Cool. So just double check. It's gone. 20 columns. Cool. So now we want to split our data. Model selection. I'm sure everyone's seen this. You can do this technically by just, picking some like int equals like 0.8. Like you could cast an integer where you multiply, this length by, 75%, whatever. I'm just going to use this, and everything in Python is kind of an abstraction if we're using open source. So in good faith, we're going to assume our buddies, our friends at sklearn did everything right for us. So we'll just use their stuff because it works. It gets the job done.
Hey, Austin, there's a couple of questions.
Oh, cool. Okay, sorry. Let's check it out. Why it won't let me open them?
I can read them to you if you want. They're in the Q&A.
Sure.
In the Q&A box. So one is, could you please remind our attendees what the Y targets were?
Sure. So what Y is if someone opens up a bank term. So if someone opens up an account with this bank, and we use the map function in dictionary where yes is 1 and no is 0. So this information describes the age of someone, their job, their marital status, these variables, and using this information, we want to predict if someone will be approved for, to open a bank account.
Cool, thank you. Another question was, is there any default way that null values are read in? Are they defaulting to 0?
There are no null values because when we call df.info, all of our values are non-null. If there was a null value, that would be up to you. And this is kind of, once again, interpretation versus explanation. So if there was a null value here, there's a variety of ways we could fix it, right? We could, we could do numerical approximation. We could use sklearn's imputers where, we could take the mean and standard deviation and, compute new values for null values. We could just drop rows that are missing information. There's a lot of things we could do if there's null. Once again, it's not necessarily out of scope because that's a good point, but for this data set, we're just going to pretend that, the data engineers and the, the infrastructure team who runs our RDBMS did great work and our data is in the perfect condition. As a practicing data scientist, I can tell you that it's not always going to be the case. More often than not, it will not be the case. But for the sake of this, to make sure that everyone's getting the most out of it, we'll make that assumption. So yeah.
That was it. Thank you.
All right, cool. Awesome. So yeah, we have it split. And once again, just we want to double check. Wait, I ran that, right? Oh, whoops. Sorry, I got distracted by the questions. X and Y test size equals 0.2. Cool. Okay, so now we have a length of this. So we give print when X train. All right, cool. So that number matches these numbers. Cool. So we did that right. I mean, I don't think anything would really go wrong in these steps, but you never know. I've had some silly errors in my life, so just always good to double check. No one's perfect, but let's do this. So this is just us, setting up what is the size of our figure going to be. This is just so it looks nice to everyone. We're going to do a correlation, which, is going to come directly from pandas. So, we don't have to reinvent the wheel. We just need to use the wheel well. That's the way I like to think about it. Oh, whoops. I should have probably told everyone, if you don't have Seaborn, once again, just pip install Seaborn, and that's going to allow you to do what we're doing. Technically, you don't need it. It just makes it prettier, which is, always a plus when you're doing visualizations. And then we're going to use my favorite colors for our correlation matrix. And then we're going to do format. So this is just a cool trick, because if we didn't put this format here, I'll run it without it. It looks really bad. Like if you push this to GitHub, you're going to get, it depends on your team, but you may get a not nice comment of, this is illegible. So to prevent that, I like to always give myself some room, and I format it to 3 decimal points. That's still not that great. So here, let's just do this. 1. All right, so these are, now this is an explainability thing. So maybe I would put a comment here and say format set to 0.1, zeros are not true zeros, but not necessary, not the significant. And hopefully you and your team have some kind of good commenting that you do. I've kind of had it ingrained into me that short and sweet is the best way. If someone has a question, normally they will ask you, but you still want to put a comment, but what we're not going to do is put, a 15-line comment that, explains why we made the choice we did. To the extent that it's relevant, this kind of captures it. The zeros are not zeros, but they're not statistically significant for what we're doing. So we just look at this correlation matrix, right? Along the diagonal, everything is self-correlated with itself, which makes sense. And we can kind of look at these highly correlated ones. So, there's a 0.8. Employee variance rate and consumer price index are very correlated with each other. Employee variance rate and your BOR3N. This makes sense because these are all numbers that come from like a governing organization. So they are I don't know if anyone does like financial stuff like stocks, but like the same underlying like thing dictates all of these values. So it's like if you invest in 5 different tech stocks, the underlying inputs to those tech stock values are tied in some, uh, in some way. So we can kind of make that assumption here that these are all highly correlated with each other. We could spend a lot of time feature engineering here right now. We could do, there's 6 ways till Sundays, 6 ways till Sunday to do this way, do this feature engineer. But for what we're going to do, we're just going to kind of say like, hey, we gave it a cursory glance. I don't necessarily think we need to, spend all of our time doing this because once again, we're in the prototyping stage. So let's just move forward like this isn't totally perfect. I mean, we could run it if we have time where we remove it, but that's part of the explainability, right? So right now we're just interpreting numbers like, hey, we relayed some numbers to ourselves. I interpreted it like, oh, okay, this is why this is not why this is me attributing, these numbers to some phenomenon. Oh, it makes sense that, government numbers are highly correlated with themselves because the government makes these numbers based off of information that they dictate they use. So that makes sense. Versus, what would be bad is for some reason, someone's age, something you literally have no control over, is highly correlated with, the employment rate. Or actually, that makes sense. Let's say it's consumer price index, or if job and age had a one-to-one mapping because they're so highly correlated, or maybe they're inversely correlated. Those are the things we're kind of primed to call out. Maybe this one month is so month has a correlation with if someone was contacted or not. So that means there's some seasonal element to this. Consumer price index and contact, there's some correlation there. Once again, I'm kind of going overboard with explaining it, but I just want everyone to know we're not glancing over this because it's not important, but this is like the prototypical stage. So with that being said, let's start our first model with rules. So
hey, Austin, there's one issue real quick. Somebody's getting an error message, module not found error. They can't locate the module Lale.
So what you want to do is here. Can everyone see this? So Command T. So here. What you want to do is what might be happening is like so this is going to tell you if you run this, I'm going to make the assumption where you're using like a Miniconda or an Anaconda environment. This is going to tell you the different environments you have. Depends on which one you want to use, but you would go Conda, activate dev. This is the one I'm using. We're now in dev. And then if you're missing Lale, you pip install Lale and you hit enter. Or if you're missing Seaborn. If you're missing matplotlib, and that will handle all the underlying dependencies for you. So I hope that helps. But yeah, so if you instantiate your Jupyter notebook with an environment that you didn't download Lale into, it's not going to path itself correctly. That's going into too much detail, but it's going to look in all the wrong places. So that's why you make sure you are in the environment that you will actually be using. So I hope that helps. But once you run that, it should work. So now we're going to use AIX260 for the first time. Algorithms. I can never spell algorithms, so I'm just going to hit tab. Feature binarizer, and then we're going to cast feature binarizer as FB negations equals true, and return order is true. Wait, true. Yeah, cool. And so this is once again going to be able to follow like the fit transform, the fit, the transform. So very sklearn-esque. the underlying math behind some of these algorithms, I'd recommend reading the ARCSID papers because it is not necessarily trivial. That being said, if you have an understanding of what's going on, it will very much help cater to kind of predefining a solution space for your development process. And that's really important. If you go into something blindly where it's like, give me data, I'll give you a model and some metric, that is, that's like, it's like giving somebody who just got their driver's license, which is your data, a Ferrari. Like, they may get somewhere more quickly than normal, but at what cost? So that's kind of an oversimplification of the analogy, but that's why it's really important. And with 2 hours, I don't think I'd be able to go over all the literature that makes these things work, but I do think it's very important that I'm showing you how to use these things, but to use them in good faith, you really want to kind of go read the papers and understand what we're doing, why we're doing it, and the edge cases. So I'm going to kind of give you guys some insights into these things to the best of my ability, but just for the sake of time, I'm not gonna go crazy. So we're just, this is our standard deviation. We're gonna cast it because this is from AIX. I can't remember off the top of my head, but I'm pretty sure this is just a clone of. No, I think that actually added some features to it, so I don't want to say that. Never mind. But basically, we need this standard deviation for one of the algorithms we're about to use. So we do F, and then we do fit, transform, and the same thing. And then we fit, transform, X tree. And then we do X test. Sorry, this is that was really bad. That was not Pythonic of me. I was using snake case and camel case, so I apologize. Transform. So cool. Boom. So what that does is that binarizes your. So as you can see, it just binarize. It's not going to show us all of it, but now we have 212 columns, which makes sense because for each unique value we binarized it. So if we do what did I call it up here? df here. If we do df.age.value, we'll be able to see all the ages. There's better ways of doing this, but the idea is for each one of these unique ages, we're going to, so there's 78 ages. So now if they're 31, instead of there being 1,947, that number is still there, but this is binarized. So this is 0 or 1. They're either 31 or they're not. If they are, it's a 1. If not, it's 0. So going back to Xtrain, feature binarizer, that should make sense of why there's 212 columns. So like 78 of those come directly from age. If you look at the data set and underlying, it will make sense. Just trust me on that. So, all right, cool. Let's actually deploy this model. Not deploy it, that's the wrong word. Let's get it instantiated and stood up. And my apologies if you've seen this data set a lot. It's just, it's a good data set to communicate the points we're trying to make, and it's also small enough for us to be able to run it without needing some kind of crazy rig. Okay, cool. So accuracy score, because that's our golden metric, and then the logistic rule regression. So what this is it's a logistic regression, but it's built on top of the rules that we make. So there's multiple ways that it does this behind the scene. It's a beam search. It is heuristic based, and then there's no, for this one it's only those two. And what it's doing is it's constructing rules based off of these rules. It creates a logistic regression around it where it uses the rules as the weights. So if you do like, if you know the logistic regression and you run it and you do log, dot underscore or whatever you call it, and you train it, you do the underscore coefs. that is what it's using rules to create these coefficients. And it does this in a way where you can give it different parameters, and what these parameters are is lambda 0 and lambda 1. And what they're going to do is, based on the values you give it, and you can automate that with grid search and things of that nature. It's going to optimize for a trade-off in model complexity and model accuracy. So based off the hyperparameters you give it, it could give you a super complex rule set that gives really good accuracy, but once again, it's a balancing act. We don't really care to get 100% accuracy if we have no idea why, or in theory. So let's get to coding it. So let's just take a rule regression, lambda 0 equals, let's choose an arbitrary number. You guys don't have to, actually you can, maybe for you guys, make this number 0.15. Or you can follow right along if you want. This is for you. So, but that'd be interesting. Maybe at the end of the talk, people could say like, "Oh, I got different rules than you," because once again, these hyperparameters dictate the the solution space. So we do this.
Hey, Austin.
Yeah.
Hey, someone here only gets 210 columns after binarizing. Is there an explanation for that?
Then